Hello and welcome everyone to another episode of Reading Club, and in today's episode we are going to explore branching part of the MIP solver. So in particular we are going to take a look at this paper, which is enhancing MIP branching decisions by using the sample variance of pseudocost. Okay, this was published in 2015 and the author is Gregor Hendel. Okay, right. So I think everyone should be aware about what pseudocost is. In case if you are not aware about it, I will very briefly cover what this is, right? So we have a node, let's say, right, in our tree. We are exploring that, and in this node we solve the LP relaxation, and one of the integer variable took this value. This is 5.3. Okay, so what do we do about this is that we simply branch. On one side we say that it is less than equal to 5, on the other side we can say that it is greater equal to 6, and we solve the LP relaxations of this two, right? So let's say the objective value for this was 7, here it is 8, and here it is say 9, right? So I can calculate how much I gained in my objective per unit change in this value of x, right? So let's say these are right bound, so here x takes value 5 and here x takes value 6, right, in this nodes. Okay, so on the left branch I can say that I gained 8 minus 7, which is 1, right? Let's say this is left branch, and my change in the variable value, which is 5.3 minus 5, which is 0.3, right? So per unit change I will gain 1 over 0.3. This much I will gain in the objective, right? So similarly for the right branch I can calculate this value, which is 9 minus 7, which is 2, and divided by 6 minus 5.3, which is 0.7, right? So these parts are always positive. We are measuring the absolute change in the value, right? So basically, like, these are my pseudo-cost for this direction and this direction, and I can basically combine them by the product rule, right? So we can just say that v minus times v plus, right? So this is my final pseudo-cost. Now if I have multiple variables which are taking fractional values, then I can compare their pseudo-cost, and the one which has the highest pseudo-cost is likely to give me most gains in the objective, so I can use that for branching, right? So that's a typical pseudo-cost branching rule. Now people don't really use pseudo-cost as it is for branching. They have some notion of reliability. Okay, so why do we have that notion, right? So people use reliable pseudo-cost as a branching rule. So what is that? Let me quickly rewind it if you don't know, right? So let's say I have this variable, and let's say its final pseudo-cost, actual pseudo-cost is this is v star. Okay, and let's say I branched on this variable first time and I received my pseudo-cost update, which is v, right? Let's call it even v1. Okay, and I branched it again, it is v2. So is this v1 be, so will this v1 be actually equal to this v star value? Probably not, right? So similarly v2 will also, like, it's highly unlikely that v2 will also be equal to v star, right? So these are like the observed value. This is like I'm saying that it is an unknown true value of pseudo-cost, right? So after like a lot of branching, this is the actual pseudo-cost value across across a lot of different branching I have learned, right? So this is like initially unknown, and I don't know about this, what the actual pseudo-cost is, but I have sampled it, right? So I have branched on this variable once, I have branched on this variable again, and so on and so forth. So I can collect these samples, and individual samples might not be equal to or even close to this v star, but if you take the average over, let's say, large number of samples, right? So let's say I have received multiple pseudo-cost updates, then this average will be like more reliable, in the sense that it is like it would be very close to this v star value, right? So the question is now, when do I start trusting this average, right? So this is basically the notion of reliability. So normally people use fixed number threshold, right? So we'll call it f and t. right? So that's what they called it in the paper. So we're also going to use that same term. So what is fixed number threshold, right? So it basically says that, you know, if you have received 5 updates, then we will call it reliable. And if you don't have at least 5 updates, then you are not reliable. If you have reliable, then you can just use this pseudo-cost, whatever is the sample average, as your actual pseudo-cost and take it for branching. And if you are not reliable, then you need to collect more data before you can use it for branching. So how do you collect more data? So instead of doing the branching on pseudo-cost, you can do strong branching, right? So just, you know, try out, basically, like branch on this variable, see what the objective gains are, and revert back that branching. So now that you have branched, you know the objective gains, and you can have your pseudo-cost update, and so you have more data, and so on and so forth, right? So once you have enough number of data, then you can start trusting the variables pseudo-cost. So if you don't trust it, then do the strong branching, collect more data, and same for all the other variables, right? So this is for one variable. I don't know, this is like not reliable, so I do the strong branching, I collect one more data. Same here, if I have enough number of pseudo-cost, then I will just take that pseudo-cost for granted. If for another variable, if I have less than that, then I will do strong branching. Okay, so this is the fixed number threshold for reliability branching, right? So in this paper, this author basically is suggesting that this fixed number threshold for a notion of reliability is not good enough. Why? Because it is not taking into account it is only taking into account the mean of this pseudo-cost, right? So it is mean, which is mu. It is ignoring the standard deviation or variance part, right? So the standard deviation or variance part should also be taken into account in order to determine whether the given average is closer to the actual value, right? So that's the plot of this paper, and we'll explore the other ways of measuring the reliability in this video, right? So let's see. Okay, so the first method is relative error. Okay, so let's say if I have this variable, and if I have received a bunch of pseudo-cost updates, I don't know how close they are to this actual pseudo-cost, right? And the fixed number threshold basically say that if you have 5 updates, then you are reliable, you are very close to this. But that's not necessarily be true, right? So that we can have updates like this, right? So we have one update here, one update here, one update here, one update here. This is like the pseudo-cost, different pseudo-cost. And if I show you this data, then suddenly you are not so confident that you know this average will be actually closer to this V star. This phi number is not good enough here, right? So you need a lot more data to confirm that this is the actual pseudo-cost. The actual pseudo-cost might as well be here or here. We don't know, right? So this is ignoring basically the standard deviation. So the first way in which we are going to use this standard deviation is through this RER rule, right? So let's see what that is. Okay, so assume that you have a standard or let's say normal distribution. Okay, let's say this is the bell curve, this is a normal distribution, right? And my V star is over here, right? So let's denote this as the mean. So this is like the distribution that my pseudo-cost updates will follow, right? So this mean is actually equal to my V star, and I don't know the width and everything, but let's say this is the mean, this is my V star that I'm trying to estimate. So initially this is unknown, but what do we know? We know that we have received certain updates, right? So let's say we have received a few updates over here, right? And let's say this one is my observed mean, right? So let's just call it V bar. So this is my observed average over my updates, right? So this value is known, obviously, right? So can I calculate the probability that my actual mean and my observed mean, right, is this is the error between them, right? So that error is between certain threshold t. So what is the probability of this happening, right? So I think if you have learned about laws of large numbers and everything, then there are ways to calculate this probability if your distribution is normal distribution, right? And that's a very useful data, right? Because now even if I don't know this mu value, right, I can be very confident that if if this is say 95%, let's say, right, then I can be very confident that my mu value is between this and this distance of my observed mean, right? So that's a useful data. So this is like more trying to be more reliable. So so for this, like obviously if you know that how to calculate this probability, right? So it requires you to calculate sigma, and you also need the number of updates, and all those things are kind of needed to calculate this number, right? So if I know this probability, then I can, this is like a way of defining reliability notion. So if my reliability notion, if this interval is super large, then I'm not reliable. But if my reliability notion is, if this interval is let's say very, very small, right? So that means that I'm highly confident that this is my actual mean, right? So this is reliable. This is not, right? So this threshold, it kind of plays the role. So of course, like I'm interested in, let's say, 95% of confidence interval. Then depending on that, I can change. I can ask, like, for what threshold will this be the 95% probability, right? So this threshold basically defines this interval, right? So that's my question. Like, so if I can, what I can do is, like, I can calculate this threshold, and if this threshold is greater than a certain number, then I can say that it's not reliable, otherwise it's reliable. So that is the relative error way of measuring this, right? So they didn't use normal distribution, they used student t distribution. So this is like very similar to this normal distribution, but there are like differences, and for that this kind of process also is kind of this numbers might be slightly different. You can calculate this probability for this also, and using that you can basically define your thresholds. Like, so these are like subtle differences. I'll anyway put a link to the description of what student t distribution is, and if you are basically like interested in learning about this, so it's kind of very useful tool as well, right? So it typically basically is used to compare two different distributions, and whether they are statistically different or not, right? So but you can basically use it in this way also. Like, you can try to measure this kind of an interval, right, and see if that the length of this interval is high or low, right? So that you need basically a t table. You can basically calculate this t value and then compare it with the value in the t table. This t table has different values for different probabilities. So if it is 95%, it's a different value. If it is 90% confidence interval, it's a different value, and so on and so forth, right? So minor differences, but the basic idea is this. Okay, so that was relative error way of measuring the reliability part, right? So there is another method that is described in this paper. It's called hypothesis reliability, right? So what's the hypothesis? So let's see if I have a bunch of variables, right? Say x1, x2, and xk, and let's say all the way to xn, right? And I have a bunch of updates for all of them, right? And so what happens is that a lot of times we can basically call a lot of these variables unreliable, and we just do strong branching on them. Now this strong branching is expensive, right? So we don't want to do it on all variables. We want to do it on variables which have like enough probability to be to basically have the highest pseudo cost, right? So if I know that, you know, this variable it's not reliable because it has only one pseudo cost update, but or let's say if I has a bunch of pseudo-cost updates, but all those pseudo-cost updates are like super low, right? So it's unlikely that its v star will be the highest pseudo-cost for this node, right? For the node that I'm considering, right? So we don't want to probably do this strong branching on this variable. So how do we address this issue? So that is by hypothesis kind of a branching, right? So let's say if I have this variable, right, it has value v star, which is for, let's say, variable k, right? And okay, we don't know the v star, but we know the observed mean v bar k, right? And it is the highest among all the other observed means, right? So this is v1 bar, this is v2 bar, and so on and so forth. Now this is vn bar. Okay, the hypothesis is this, that let's take a look at x1 and take a look at xk. So xk, I know that it has the highest pseudo-cost for the observed means, right? But let's say I'm also interested in x1. So my hypothesis is that x1 basically it has this observed pseudo-cost v1 bar, right? And my hypothesis is that v1 star, right, is at least greater or equal to vk star. So this is the hypothesis. So obviously I don't know v1 star, I also don't know vk star, but I'm making this hypothesis, which basically means that it is better to branch on x1, right? And what can we do about this hypothesis? There are two things, right? We can reject it, or we can accept it, or we can test it, right? So test it basically means that I can basically do a strong branching on x1 and on xk and see if that is more likely, right? So this part is, let's say, call it the strong branching, right? This testing is expensive part. So this is an expensive test, but can we have something which is cheaper test, right? So let's this is also again done using student's t-test. T-test. So what does that t-test look like, right? So t-test basically it also takes into account this mean. I have how many number of updates I have, and what is my standard deviation, right? For this one, and also for this one, right? So I have three numbers, n1, sigma 1, and v1, nk, sigma k, and vk bar, right? So using those 6 numbers, I can calculate what is the likelihood that this. So both of them are like two different distributions, right? So one of them is this distribution, and the other one is, let's say, this distribution, right? So do we have enough statistical evidence that these two distributions are different, or this particular, like this distribution has a higher mean than this distribution, right? So for that you can use this student's t-test, which basically calculates a t value, right, using all these 6 numbers, just basically combines them in such a way, right? And using this t number, and you can basically compare it against t table. So using those 2 numbers, right, so this t table will give you different entries for 5% error, 10% error, and so on and so forth. So let's take a look at 5% error, right? So if this t value is comparable, it's basically like higher than this 5% error, that means I'm like more confident that these distributions are significantly different, then basically I can reject this hypothesis, right? So this is like a cheaper test compared to strong branching. So if I can simply just reject this hypothesis, right, in that case I don't have to do the strong branching. But if I can't reject this, then I'll have to do the strong branching, right? So this will basically ignore avoid doing this test on this type of variables, right, where I know that this x, let's say, let's use m, right? So this xm, right, its distribution is, let's say, over here, right? So this is like I can be like very confident that I don't know that I'm definitely, this is not reliable, but it's very unlikely that its pseudo-cost will be higher than this blue or red distribution, right? So for that, I don't have to do the strong branching. So that's hypothesis branching. So I make a hypothesis and I do this test using this t-value, and I can basically do it with all variables, right? So all pairs of variables, and if basically it basically filters out a bunch of these variables, and for the remaining ones I can do the strong branching. So my strong branching, I have to do less strong branching for like fewer variables basically, and that's why I can be faster, right? So that's another notion of reliability. Okay, so far we have seen three ways of measuring reliability, right? So this is fixed number threshold, this is relative error, and this is hypothesis testing. And these two basically make use of students t-distribution and t-test. And again, like if you don't know about those particular distributions or tests, I basically described the high level idea. But if you are interested in knowing about those tests and distributions, I have put a link in the video description. Okay, so check it out. So now it's time to evaluate how do this perform, right? So they basically evaluated on skip. Okay, and for evaluating them, they did a bunch of things, right? So first of all, they disabled all heuristic, right? So why? So these heuristics are kind of noisy. So we are basically trying to evaluate something that is affecting branching part, right, in the MIP solver. So we want to only evaluate the branching part, and there are a lot of components in the MIP solver that can like interfere with branching, right? So these heuristics can sometimes find feasible solutions, and that can affect the branching part, right? So we don't want that, so we basically they disabled it, right? And another thing that they did was node selection. So node selection was depth first search. They fixed it to this, right? So this is not the default node selection strategy, but for evaluating the effects of all these things, they did this. And the last thing that they did was provide best solution, best known solution. Right, so this is another trick. Like they basically only care about the bound improvements, right? So they basically evaluated their benchmarks on MIPLib, right? So three different versions of MIPLib, 3.0, 07, and 10. So this MIPLib has a bunch of instances, and for a lot of them, we know the best solution already, right? So some of them we know the optimal solution, some of them we don't, but for best solutions is kind of known for all those instances. So they basically provided those solutions before the search tree began, right? So they're only measuring the effects of improvements in the dual bound, right? So let's see how these things compare, right? So this is the default one, right? So compared to that, when you compare on all of these instances, right? So basically, also we have to ignore everything that is not even entering branching, right? So something is getting solved completely in the pre-processing stage, then we don't evaluate it. Basically, we ignore it for the statistics, right? So here, the solving time was higher, right? And the number of nodes was lower for relative error. So they again like had like 4 or 5 different versions for different percentage of confidences, right? So this is what they observed. The time was sometimes slightly higher, not so high, but the number of the reduction in the number of nodes was very high, right? So this reduction was very huge. For the hypothesis, there were two cases, right? So there were easy and there were hard instances, right? So hard means like it took way too many nodes, and easy means like fewer nodes, right? So on the easy instances, so here also they have for nodes, right? So number of nodes to solve that prove optimality was significantly reduced for all instances, but for easy instances the time was slightly higher, and for the hard instances the time was slightly lower, right? So that's this is how they measure the effect of all both of these ways of measuring reliability. So now they are actually like written in script. I'm not sure if they are enabled by default or not, but they are at least present, and to some extent they are being used as well, right? So this is how they measured it. They also measured a dual integral, right? So there was significant reduction in both cases, right? For this one and this one on dual integral. So what's dual integral? So if you know that this normally your primal has this kind of a curve, primal bound, and there is also this at the same time you are also changing your dual bound, and when these two meet, that's when you have proved optimality, right? So this area is your dual integral, right? And if you compare, why do we sometimes compare? Because let's say if I have one method doing this and the other method is, let's say, doing this, which is basically proving optimality before the blue instance, but the dual bound is not improved for a very long time, then it's bad, right? So that's why you basically measure this area under this curve, which is your dual integral, and that is like significantly lower for both of them. Even though sometimes the time to prove optimality is higher, but again, like this was under these conditions, right? So these experiments were done under these conditions. In that paper, they haven't really provided the results of default mode, right? So where the heuristics are on, the node selection is the default strategy, and you don't provide this best solution, right? So when you remove all these things, then you are under the default conditions, and we don't know the results about that. But looking at the evidence, it kind of seems that these two methods are better, and obviously because they are basically making use of standard deviation, whereas this one is not, right? So that's all for this paper, this video. So basically we learned two new notions of measuring reliability for pseudo-cost that is basically used in reliability branching, right? So thanks for watching. If you liked this video, hit like and share it with others, and otherwise we'll see you in the next video. Bye.